So in the last lecture, we have tried to motivate you guys why anomaly detection is an important problem, and what are the potential applications of anomaly detection in the context of social network and other context as well. So in this lecture, we will start off by looking at a taxonomy of the algorithms that have been proposed for anomaly detection, and then we will look at some of the skeleton algorithms that have already been there, and then we will look at specifically few algorithms which have been considered as state of the art, as baselines, not state of the art, but at least baselines in the context of anomaly detection. Okay. So this is the taxonomy. As you see here, in general, we divide the algorithms into two categories: static graphs, so algorithms which are designed for detecting anomalous entities from a static graph, and algorithms which are designed for detecting anomalies from dynamic graphs. Now, if you look at the static graphs, there are methods for plain static graph in which there is no attribute associated with nodes and edges, and there are algorithms specifically designed for attributed static graphs, right? And both the plain and attribute, both for plain and attributed static graphs, there are algorithms which only look at the structural properties of the network, and there are algorithms which also look at the communities within a network, right? Basically, the idea is that we cannot detect outlier by looking at the global structure of a network. Rather, we should focus on different subparts of a network, different clusters of a network, and then with respect to a cluster, we can define anomalous, we can define anomalous entities and then identify them. Okay. So we will discuss one such algorithm which will take care of the community structure and detect the communities as well as the anomalous nodes simultaneously, right? And then we have algorithms which will which also look at the relational types. For example, look at the relations between entities and based on that detect anomalous entities, right? With respect to the dynamic graphs, we will look at again plain dynamic graphs, feature based, decomposition based, how we can decompose a network into subnetworks and look at the changes, right, of behavior of networks in subsequent time periods, and based on that detect anomalous entities which should not have been there, but due to some behavioral change those entities exist in the network. Here also we look at community based approaches and we look at window based approaches. We in the dynamic network, since we have static snapshots of a dynamic network at different points in time, we fix a particular window and we see within the window what's the normal behavior, and we keep moving the window and we'll see that what's the abnormality across two subsequent windows, and based on that we come up with some metrics and then we detect anomalous entities, right? So I will not cover each of these types in this particular chapter. Rather, I will give you an overview of each of these types, and then I will focus on few specific types, right? For example, I focus on one algorithm which was designed for community based approach, community based outlier detection. I will focus on an algorithm which will look at dynamic graphs and based on window based approach detects outliers or abnormal entities, right? Okay. So let's look at the static graph. Okay. So in the static graph, what is the problem definition? We are given a snapshot of a graph, right, a plain graph or an attributed graph, and our task is to find nodes and edges, right, and substructures that are few and different or deviate significantly from the patterns observed in the graph. Okay. And this is again the broad definition, but we will try to make it concrete. And in this particular category, we look at plane graphs and attributed graphs. Okay. So, let us look at the plane graph and the algorithms which which extract structural based features from the plane graph and detects anomaly, right. So, if you look at the static graph and those algorithms which look at the structural based properties, we will see two kinds of properties that are generally used. One is a simple feature based approach where we extract node centric features, subgraph centric features, and then we build normal classifiers. And then in the other approach, we define something called the proximity of nodes, right, in a graph, and then depending on the, so proximity is basically similarity between similarity or distance, right, between a pair of nodes, and if a node is far from the rest of the nodes, we can categorize those nodes as anomalous nodes. Okay. All right. So, let us start with a very simple approach, feature based approach. Okay. So, in a normal graph based setting, we look at 5 different types of features. The first one is node level feature, and we look at features like eigenvector centrality, closeness centrality, betweenness centrality, local clustering coefficient, and degree associativity. Now, all these metrics have been discussed already, right, in the second chapter, I guess. Okay. So, and all these features are node centric features. So, what you basically do, you extract these features for individual nodes, and then you can come up with some classifiers, and these features would act as normal attributes, and then you can and then you classify. Okay. If you move from node level to further coarse grain level, we can look at dyadic structure, properties of a pair of nodes, right. We can look at the reciprocity. Reciprocity is again the extent to which two nodes are connected to each other. So, for example, if there is an edge from A to B, directed edge, whether there is another edge from B to A or not, this is reciprocity. We look at edge betweenness. Edge is basically a dyadic property, right, edge connects to nodes. We look at edge betweenness centrality. We also look at the number of common neighbors. We can look at, say, Jaccard coefficient between a pair of nodes. We can look at the whole bunch of metrics that we discussed in the link prediction chapters, atomic adder distance and so on. Okay. Then we move again from dyadic structure to some sort of ego network structure, where we look at ego network. We already know what is a ego network. So, an ego network consists of an ego, which is a node, and its one-hop neighbors, the induced subgraph of the one-hop neighbors, right. We look at the node and its one-hop neighbors, and we also take their connections, and that basically forms the ego net, and then we extract different features from the ego nets. For example, we extract number of triangles, number of total weight, right, principal eigenvector, eigenvalue, and so on. We will discuss these properties later on, and that would determine the property of either a substructure or even the property of a node, right, of the ego, for example, right. Then we move from ego net to a community based or a group based property, where we look at, say, density of a community, right, actual number of connections divided by the possible number of connections. We look at Newman's modularity. We can measure Newman's modularity. We can also measure conductance, we can measure permanence, cut ratio, and whole bunch of metrics that we discussed in the community detection chapter, right. And if we are also interested to look at the graph based properties, right, the overall graph based properties, we can measure number of connected components, right. We can measure the distance of the distance of different components, and we can also look at the size of the components. We can look at the principal eigenvectors, we can look at principal eigenvalues, we can also look at the weights of a minimum spanning tree. For example, the graph is weighted, we can extract minimum spanning tree, and from minimum spanning tree we can check the weights of edges, and we take the sum of weights of all the edges. We can also measure the average degree of a node in the graph. We can also measure the global clustering coefficient, right. All these measures are global measures, right. And then we can simply employ classifiers like naive Bayes, or even logistic regression, or support vector machine, and classify nodes into anomalous and non-anomalous, anomalous and normal nodes, right. Okay, now let us look at the one such method which takes care of the features that we have discussed so far, right, a subset of features that we have discussed so far, and identifies anomalous entities. Okay, I think this is one of the first papers on anomaly detection in graphs, right. This was published in PA-KDD, I think way back 2008, 2009 by Leban, Akoglu, Christos, Falustos and their group. Okay, and this is one of the algorithms which detect anomalous entities in an unsupervised manner. Okay, all right. So the name of this algorithm is called oddball, right. What it basically does? It basically extracts, first it extracts egonet for each node. It takes a node and its corresponding egonet, and egonet constitutes the ego and only the one hop neighbors and the induced subgraph out of all these nodes, and then it basically extracts different measures of the egonet. Okay, we will discuss what kind of measures they generally use, and then it basically tries to look at the relations between these attributes of egonets. Okay, and they hypothesize that if a node is anomalous node, right, its corresponding egonet structure exhibits a completely different properties, right, which is not there in a normal kind of ego network structure. Okay. So according to their paper, they discover several new rules, right. We will discuss these rules, right, in the density, in the weights, in the ranks and the eigenvalues that seem to govern, right, the so called neighborhood substructure, which is the egonet, right, and they also show how to use these rules for anomaly detection, right. So now let us look at this algorithm carefully, and this is very simple algorithm, but it turned out to be very useful in certain context. Okay. So as I mentioned, anomalous entities, defining anomalous entities is challenging. Therefore, they simply started off by saying that, look, we are not interested to extract all possible anomalous entities, rather we are interested to identify 4 types of anomalous entities, right. So one is this clicks. So click or a near click is basically anomalous, because generally a graph doesn't contain click like structures. So if we see a click, right, it is basically an anomalous, it may be considered as an anomalous entity. Similarly star, the star like structure is again very rare, right. So if we see a near star, right, it can again be considered as anomalous entity. They also define something called heavy vicinity. So let us look at this figure here, right. So you see that this is a near star, right. There is this central node and there are peripheral nodes, right, but again this is with respect to the egonet. Okay. This egonet looks like a star, meaning that the peripheral nodes are not connected in that sense, right. You see that there are only two edges among the peripheral nodes, right. Similarly, you see a near click. Okay. Here this is the egonet node and one of neighbors, and almost all the neighbors are connected. The third the third entity is called heavy vicinity. Okay. Now, what is heavy vicinity? So, they basically defined heavy vicinity with respect to an example, right. So, what they said, I am quoting this thing from their paper. What they said is that if a person, I mean, let us think of a who calls whom network. Okay. There are individuals, and if somebody calls some other person, there is an edge from that person to that person. So, person X to person Y. Okay. Who calls whom network. So, in the who calls whom network, if person I has contacted n distinct person, n distinct people in the who calls whom network, we would expect that the number of phone calls, which is essentially the weights, right. Think about it. So, say this is the ego and these are the alters, right, peripheral nodes, and this guy is calling these guys. Okay. And if and the weight associated with an edge indicates the number of times ego has called an alter, right. So, this is 5 means this guy has called this guy 5 times, and so on and so forth. So, right, we would expect that the number of phone calls, which is the weight, right, would be a function of n, right. So, the weight is it should be order of n. N is the number of peripheral nodes, number of alters. Okay, or you can think of it as number of nodes in the ego net, because basically n plus 1 is order of n, right. So, then they said that extreme total weight for a number of contacts n would be suspicious, right. Now, think about it. Say you see that this guy has called lots of times to a subset of his alter nodes, his neighbors, right, lots of times, which is not simply an order of n, right, that is suspicious, right. For example, in who calls whom, it can be just a faulty equipment which basically forces redialing, right, and therefore called calls have happened automatically, right. So, this is called heavy vicinities. So, the fourth category is called dominant heavy links. This is again related to who calls whom network. Now we are looking at individual weights of edges, and if you see that one edge has a lot of weight, right, compared to the other edges, then there is some problem. Okay. So, in a who calls whom scenario, a very heavy single link, right, in the one step neighborhood of a person I is also suspicious, okay, indicating, for example, a person that keeps on calling only one of his or her contacts an excessive count of times. Okay. So, this is the dominant heavy link. You see that this link is very heavy, okay, and therefore, the edge weight would be a lot, edge weight would be much higher than the remaining edge weights. Okay. So, they wanted to detect these 4 types of categories. Okay. All right. So, now let us look at what are the features that they have considered. They have considered, remember, they have only looked at the ego network, right, and they have considered the number of neighbors, okay, which is basically the degree of the ego. Then the number of edges in the ego network. It is not the ego, it is not the degree of the ego, because it is the induced subgraph, neighbors are also connected. So, EI is the number of edges, and then we have total weight of the ego net, which is sum of the weights of all the edges, and the fourth one, lambda, is the principal eigenvalue of the weighted adjacency matrix of ego net I, right. You have this small ego net, you can get the adjacency matrix, weighted adjacency matrix, you can get the principal eigenvector and the corresponding principal eigenvalue, right. So only these are the properties that they have considered. And what they claimed is very interesting. They claimed that if you look at the relationship between E and N, right, E and N, that would help you identify cliques and stars. Okay. Secondly, if we look at E and W, right, that would help you identify heavy vicinity kind of anomalous entities. Okay. If we look at W and lambda, right, that would help you identify dominant pairs, right. You may wonder how they have concluded these things, right. Let us discuss. Okay. So, the first observation is that if you look at the relationship between number of nodes and the number of edges in an EGO-net, it should follow a power law, right. So, according to them, EI should be proportional to Ni to the power alpha, where in a normal case alpha should vary between 1 and 2. Okay. So, right, and in a normal case, what they said that although alpha varies between 1 and 2, but the ideal range is 1.10 to 1.66, right. If you see any entity which does not belong to this range, they are suspicious. Okay. So, let us look at an example, this one, right. So, they have tested this on multiple data sets. The one is called post-net data set, the other is this Enron data set, and the third one is Oregon data set. I am not explaining the data set properties and all, you can look at the paper, but I am just telling you the observation, the major observation. Okay. All right. So, what is the first observation? For example, one entity was Ken Lay, who was the CEO of Enron, right. Obviously, he is an exception, so he is an outlier, right. So, there is no ground truth as such, but they tried to evaluate their method based on some manually inspecting some of the entities which do not belong to the standard deviation or the normal range that should be there, right, in this particular case. So, what they said is that if you look at entities which are here, right, which fall even below the slope 1 or just above the slope 1, they are kind of star like structure, right. And if someone some point lies on the slope 2, right, or above much above the standard deviation, that entity may look like a the clique like entity. Okay. So, in this way you can identify cliques and stars. All right. Let us look at the second observation. In the second observation, they tried to differentiate heavy vicinity from the remaining population, and what they hypothesized? They hypothesized that total weight, right, and the number of edges EI, right, these two features should follow a power law. Okay. And according to them, this power law, this beta is this beta should basically beta should be 1.29, right. So the range beta should be up to 1.29. If it is above 1.29, then there is some problem. Okay. And in the similar manner, they plotted the number of edges in the x-axis and number of weights on the y-axis, right. You see these black dots, black circles, the best fitted line, red line, standard deviations and outlier points, right. again their conclusion was kind of same, that those points which are far from this standard deviation, they are most probably outliers. Okay, I mean outliers, and their type is essentially heavy vicinity. Okay, so let's look at the third observation. What they said is that there is again a kind of power law relation between the principal eigenvalue lambda of the egonet of the weighted adjacency matrix of the egonet and the total weight Wi. Okay, and basically the idea is same. You plot it, and if you see that the points are far from the standard deviation, they possibly indicate that the structure is a kind of a heavy dominant pair like structure. Okay, so visually this is very very interesting, right, to look at, but how do we do this thing automatically? Okay, so what they proposed is that you have all these features, right, so you have 4 basically features, and you have all combinations of features, right, xi, yi. Okay, so what they defined something called outlierness score, right. So outlierness score of a particular node or a particular egonet, does not matter, same, right, is defined by max yi comma c xi theta by mean yi comma c xi theta times log mod yi minus c xi theta mod plus 1. Let me explain what it is, right. So for every node I, you have a pair of features. There are 4 features, and you can have 4 C2 pairs, right. Let's say one such pair is xi and yi, one such pair. Say xi is ei, number of edges, and yi is ni, number of nodes. Okay, then what you do? So normally yi and xi should follow power law, right. So yi should be proportional to xi to the power theta. Theta is the coefficient. Depending on this observation that we mentioned, theta can be anything. Theta can have certain range, right. So c times xi theta, xi to the power theta, right. This is what? This is basically the fitted value, right. Since you based fit using a line, right, log scale. Remember, in the log scale, power law behaves a line, right. Power law is basically behaves like a line. So in a log scale, cxi is the projected value, right, the based fit value, right, and what is yi? Yi is the actual value, right. So essentially yi minus cxi theta is the error, right. Now in this particular formula, you see that there are two times that we are penalizing if there is an error. This is one component of the error, and this is another component of the error, right. This is a simple max mean normalization, right. The higher the deviation, the higher the numerator, right, and this is again another error component, but in a log scale, right, and the higher the value, the higher the outlierness score, isn't it? This is one way of capturing the deviation, right. You can have another way of capturing the deviation, but this is a very simple way, very effective, scalable, right, unsupervised. Therefore they propose this approach, okay. And then you do not need to look at it visually, you just calculate this value for each entity, and then you rank all these entities based on this outlierness score, and then you return entities whose outlierness scores are higher. Okay. So, this is about oddball. I strongly suggest you guys to read the paper, fantastic paper, but you know, lots of interesting ideas, but those ideas may not be useful in today's context, I mean in the context of deep learning and stuff, but this was really a nice paper. I think this paper got the Taste of Time award in the last year PAKRD, if I am not mistaken. Okay, this is really a fantastic paper. So, you can also look at, so that was basically a feature based approach, right. In the next lecture we will look at proximity based approach, right, where we see, you know, how these two nodes are related, how they are different distance wise and so on and so forth, and based on that we will try to identify outliers. Okay. With this I stop this lecture today, and then in the next lecture we will discuss the following part of the chapter. Thank you.